Hey guys, welcome to chapter 2 of calculus. And here we're going to learn about the fascinating derivative and the tangent line problem. And just so you know, I haven't taught this in like a couple of years, and I haven't prepped because I kind of wanted to see how I could do it if I just wing it. So see if I still got it in me. Plus, it's funner this way, but I apologize in advance if this turns out bad. But just have faith, please. Here we go. So it's derivative in the tangent line problem. Let's look at my notes from back in the day. Pretty cool. So back before life and the universe was first born, or maybe not that far back, but like calculus was all about this idea. Like up to now in your math lives, you have straight lines. You're like, yeah, it's got a straight line. The equation of the line is y equals mx plus b. And that's all you ever get when you're in your math life, and you're like, yeah, no, I know how to solve every problem in the world, but not really. And in fact, almost none of them. Because actually, most things in the world are nonlinear. I think pretty much all of them are nonlinear, except for human-made things. But that's a whole different debatable thing. But so the question is, how do we deal with phenomena or things that don't make a straight line? So let's maybe make a graph. Let me make it better than that. Ruler. So we're gonna look at a curved line. Let's look at a standard parabola. We all love and know. Let's do this. All right. X, Y. All right, and then we have the famous parabola that's a curve-looking line, right? Y equals mx plus b, or y equals x squared, or f of x equals, well, let me write it, actually f of x. F of x is equal to x squared, right? So what's the slope of a line like this, or a curved line like this parabola, huh? What is it? Well, it depends where you look, because it changes. Let's pick some points here. Let's say that's 0, 0, which it is. And 1, 1 would be like maybe right here. And maybe 2, 4 or something would be like way on yonder over here. This for example. Well, it's not. Well, yeah, we'll just say 2, 4, even though it's not really the scale. But now it's the thing is, see the graph here, and that's actually, let's pick a point over here. What the? Let's come to life. Let's pick a point on this side. What the heck? Come on, parabola. Let's pick the opposite end. Now we're getting crazy. -1, 1. Pretend those are even. Because we can see the graph is decreasing here. It's going downward. Then here it goes. It gets flat, sideways. Then it goes up. It goes up even more, steeper. So like the steepness changes. The rate of change of this parabola changes. So the rate of change changes, really. So it becomes more complicated to describe the slope because the slope is not constant. So we came up with this ingenious trick. By us, I mean like other people named, I think, Isaac Newton and some other guys. Oh, I let him take the credit. He like invented calculus over like a winter break or something. That's what they did back before TikTok and cell phone. But we're still going to be using straight lines because that's all we really understood. We still really kind of do. But let's say we want to understand what's going on at 1, 1. So it's like, theoretically, we want to figure out like the slope of a line like this, right? Let's make it blue. Like, what's the slope of this line? Slope equals what? What? Because we don't know, we can't really be sure, because we're just kind of making a guess. And the thing is, since we have 1 point, how are you going to find the calculated slope when you got 1 point? You need love. Remember, slope equals the difference between the y coordinates over the difference in the x coordinates, right? So we're stuck when we have just 1 point. What? Dang. But then peoples like Newton and some other guys came up with like this other thought. They're like, let's take a line with 2 points. So let's switch. What color should I pick? Let's pick blue again. Let's pick green. Oh yeah, I got Panda Bear. She's a little shy, so she's still in her little protection sheet. But yeah, say hi. She's a little shy, but she'll talk later. So we pick a line that kind of goes through there, or close. Let's say like let's actually pick these ones. Because then arguably we could be like, well, the slope of this green line is probably equal to the slope, is somewhat close to the slope of the blue line. Let's say the slope of the blue line is, let's say M, or M1. Slope of the green line maybe is about M1, but we know it's not exact. But we can figure out the slope of the green line because we can actually find the differences. Where'd my green marker go? What the heck? Oh, there it is. So the slope of this would be 4 minus 0. 4 minus 0 over 2 minus 0. So about 2. And that green marker is dead. Let's throw it away. Money. But it's not 2 exactly. So we just keep on getting closer and closer to this point by making more and more lines. So let's pick another point here. We picked like a point here, a line that went like that. Maybe it goes through this point here. Let's call it A, and this one B. And so the slope of M1 is going to be pretty close to the slope of line AB, right? Yeah. And if you get closer and even closer, let's hypothetically theoretically get so close that it's basically indistinguishable from that line. So let's say C and D, right? And we can basically say this M1 is equal to slope of the blue line is equal to the slope of CD. We're so close that it doesn't really matter. That basically it's so close and useful and approximate that we're not going to notice any errors or we're not going to have any problems by using it. So that's the idea. Seems simple enough, hopefully, but let's actually do like calculations with the form because that'll make it make more sense. Hello, Odie. Hey everybody. So let's look at line. Which one should we pick? Okay, so, all right. Let's break this down. Let's erase this for now because we want to have a formal way to write it. First, we're going to look at the equation mathematically, formally, like without any numbers. Then we'll do an example. We have our y-axis. That was very bad. Our x-axis. And whatever this line looks like, f of x, we'll say. Well, let's go further. Let's go f of x. We want to find the slope. Make this more smooth. Let's say we want to find the slope over here. Let's see what this book depending on your textbook and your course, you may use C or H, but this one uses C and X. Interesting. And we use point of slope. So let's call this point. But now it uses X. Now I don't know which side to use. Let's just go with C. Okay, we'll do that. So let's have this point be c comma f of c, right? That's the coordinates it has. So we want to find the slope here. Let's go with the slope of. Let's put it over here. Slope of the line that goes through C. So let's call that slope of the slope M of the secant line. Before you spend a while, bear with me. I want to make sure you use the correct form. Actually, let's just go straight to this. The slope of the tangent line. Slope of the tangent line at point at C comma f of C is, so we're going to put equal to, and we use this quick one called the derivative, f prime of x, or f prime of C. This will be equal to, it's still like in rise over run. So let's pick another point over here. Let's make it a little farther actually so we can see it better. So let's have a point up here. We'll call this, we're going to call this C plus whatever difference we take to go this far, because we're moving a little bit to the right. Let's make this difference delta x. So delta x is this length from here to here, right? So this coordinate is C plus delta x. Yeah? And then the y coordinate will be f of C plus delta x. F of C plus delta x. Right? Again, it'll make much more sense when there's a number, but think about it. It's just x, delta x is this length. That's just C plus delta x, is that's just the horizontal. And from all the way here to there at the top, that's what f of C plus delta x is. This length right here is f of C plus delta x. It's the y value. Now, that's all we do. This is like y2. This is x2. This is our x1. This is our y1. So it's just going to be y2 minus y1, or f of C plus delta x. Minus f of C in red. Yeah. Over x2 minus x1, or C plus delta x, minus x1 minus C. And this ends up being, erasing this, the top stays the same. This is a weird feeling marker. F of C plus delta x minus f of C. Using all black markers now. Over, these C's cancel all over delta x. And this is known as your derivative equation. Say f prime of x. That's the slope of the tangent line. Of a line, whoa. Of a line that would go through here and here. But again, if we say tangent line, it'd only go through one point. So what we do is we say, theoretically or mathematically, we want to smash this distance so it gets to 0. These points get so close to each other that this point, is basically on top of this point because it scoots to the right or this scoots to the left. So these points are essentially the same. So let me maybe do another little side picture here. They get so close that these points are one is over on top of each other. So they're the same. So the difference, delta x, this delta x as delta x goes to 0. When delta x goes to 0, if this is 0, they're on top of each other because there's no difference. And so we adjust this equation to the ultimate equation, and let's write, I don't like that marker. Let's write it officially over here so you can see it. So the limit, we'll say the limit, yeah, we did the limits, of course. zero. Actually, right here. Even though I don't like that. The f of f prime of c is equal to the limit as delta x goes to 0 of this, of f of c plus delta x minus f of c. What's minus f of c? All over delta x. There you go. I hope I did an okay job with that. But it really is the basis of all calculus, so it's not going to be something you can I can brush over through quickly. But when you think about it, it makes it beautiful, as all things, or as most things in math. But now let's do some calculations using it. Right, Panda? Here you go. Okay job. So feedback is always helpful. I know I'm working on it, but I need to improve it. Just please, feedback. Let's find the derivative at a point. So let's look at how we would use that. Let's do absurd, basic, more simple one. Okay, I got one. So how about them Lakers? How about them Cowboys? So let's do 2. I got one. So using this, I'm erasing this now, all right? You cool? Yes. So let's find the derivative at so find f prime of x at the point 1, 1 for the graph y equals x squared. So we have f prime of x, or in this case, c is going to be equal to 1. This is c, f of c. So c equals 1. So f of 1 is going to equal the limit as delta x goes to 0 of f of 1 plus delta x that one red, minus f of c minus f of 1, all over delta x. Now, well, it's like, what the hell do we do here? We do some math, that's what we do. Now, here's the thing. We want to break this down in a way that's going to be like, we'll cancel some stuff out. I'll show what the graph looks like at the end, because I don't want to give it away, or I don't want you to get used to that, because it may make you try to approximate it or guess at it. So what happens here is this part is the function equation. The function is x squared. So here we have f of this squared. So whatever is in here, we square, because that's what the function is. So we're going to have 1 plus delta x squared, because that's what the input is. The input here is x, the input here is this whole thing. 1 plus delta x, yeah? Yeah. I don't know if that's more confusing, or if that makes sense. But make that squared minus f of 1, because here it would just be minus 1 squared. Minus 1 squared, which is just 1, all over delta x. I should put the limit here again, but I'll do it after. Professors get very annoyed if you don't put the limit in every step, so just know that. Warning, beware. So we just now do some math, algebra. So 1 plus delta x times 1 plus delta x. I'll write it out step by step, but if you can do it in your head, that's great. But the main thing when you're dealing with this, just treat delta x like you would a variable. Multiply it squared by itself. Minus 1 all over delta x. Going down to here. So we go 1 plus 1 delta x plus 1 delta x plus delta x squared. We get 1, so plus delta x plus 1 delta x plus 1 delta x plus delta x squared. Oh man, it's getting dark. Ah, we'll be back. Be back in a flash. Come on, light. There you go. Still here? Come on, there you go. All over delta x. Now, this is just 1 plus 2 delta x. 1 plus 2 delta x. I love delta x. Look at this square, or this triangle looks awesome. Plus delta x squared. Wait a second. Did I miss something? 1? Oh yeah, minus the 1. Whoops. Let's make this in red at the very end. Minus. Oof, I'm screwed. Minus 1 here, so these ones cancel. That makes sense now. Over delta x. And so then we have 2 delta x plus delta x squared. And this is where you can factor out the delta x. Again, just think of it like a variable. So delta x times 2, don't mind those drop markers, plus 2 plus delta x all over delta x. And again, think of this as like a z or a variable. Delta x's cancel. Where did I go? And let's write the limit again, because we need it. So limit, what the heck? I'm too excited. This is fun. I'm doing calculus there. Oh man, the joy it's bringing me. You guys are so lucky to do calculus. Don't take this part of your life for granted. The limit as delta x goes to 0 of that of 2 plus delta x all over 1. It's like a fraction. So delta x goes to 0. Hey. So this goes to 0 and 0. So what do we get? Just 2 over 1, which is just 2. So the answer is 2. Hell yeah. 2 is a great number. Heck yeah, it's awesome. So slope is 2 at that point. Slope of the tangent line is 2 at that point. Shall we draw a picture? Yes. Can I erase this? Yes. That's like a video. Oh crap. Well, whatever. It's all good. So drawing our sketch. It's power mode. Bang. 1, 1. So 1, 1. We're wondering what the slope of this purple line would be. So the slope here, or f prime of 1, or the slope here, is equal to 2. Basically saying that this has a slope of 2. So if we were to go down, going down 2, what the heck? That would be going up 2 to the right 1. If you were to actually graph it all more completely, this would intersect at 0, negative 1. That's what that tangent line would look like, drawn, perfectly. So the slope of this tangent line, so this is y equals 2x minus 1. And purple line is tangent. Yeah. Dang. I mean, math's coming back, even though I haven't done it for like hundreds of years. That's what math is all about. Okay, so should stop there. Where are we at? 23? Yeah, I mean, just one more thing, but you don't have to stay, but it would be great because these are a couple things that you will need to know, and I'll do some more examples. Let's see, scrap of the chart. Actually, let's stop it there because I'll do this in another video because I want to do another more complex example. Because it'll make more sense, I guess. Find the derivative of the function and graph the sharp turn. Yeah, I'll do more examples that show all the types you will need to know for the most part in the next video. So hope that helps. If it does, please say that you're thankful in some way by subscribing and by liking. And if not, still do it and then give me feedback and feel free to criticize, but in a nice way. See you guys in the next video. Bye.